Now that you're familiar with the process of building models, let's go into how to fine tune these models. So the new piece that we're going to work on today is this do parallel package. We're going to keep using the caret package. I'm using the same data as before, so all of this data setup is the same. One thing I wanted to point out that can come up later is this is the distribution of the ROA in the subsequent year. And notice even after removing some of the outliers or moving them in, Windsorizing them. So notice this is, if it is less than the first percentile, then set it equal to the first percentile. Well, even at that, the lowest ROA is minus 17, right? That would be whatever, let's see, 1, 2, so negative 1,700% for ROA. So that's really unusual. Doesn't seem like something we would expect. So we could possibly try and change this some more too, but we'll go ahead with it as it is. Okay. So I'm doing the training sample as 60% of the total sample, and then creating the rest from as the testing sample. And I'm just using these variables, the y variable, ROA, lead 1, and then all of the x variables here. So I want to show you the effects of running it in the analysis in parallel. So here I have the analysis not run in parallel. Then if we go down here, it's the same model, exactly the same. The difference is that the second time I run it in parallel. So if I don't run it in parallel, that means every tree that it's created, and I'm using random forest because some models could be faster or slower. Random forest is quite slow. And this is because it has to create every tree from scratch. So if, let's say it's running 1,000 trees, and it has to go through each one of those one at a time. And when I run this, notice it's more than an hour and a half, right? It's almost 2 hours, or, sometime, I can't do the math in my head right now, but hour and a half or something that it took to run this. So I wouldn't run this if I were you. Then let's do the parallel part. So what happens in parallel processing is if you have units that can run things separately. So this can happen, you can have computers that are clusters, different computers that it can be run on, or your own computer might have different processing units, and if that's the case, it can run them individually. So here I have 16 cores on my machine. You can do this detect cores to see how many you have on your machine. When we do this, you don't want to use all of the pieces of your machine, all of the cores, because then it'll use up everything that your machine can do. So probably don't want to do that. So notice I have 16 cores, so I'm using 12, so using almost all of them. If you have one core, then you won't be able to do this. The machines in the labs, I don't know what they have, but at one point they had like maybe 4 or 6, so you just use some portion of those. So this is to create those, or to create the clusters. This is the make clusters, so it's going to assign them to different pieces. So I'm going to assign my computer into 12 different pieces, and then this register do parallel is to say, go ahead and start these, and so we're going to use all of these pieces. So once we have this going, your R is going to treat them as all separate units and start to use them. When we're done, we have to tell it to stop, which we'll do later. So when I ran this, notice instead of looking at hour or more time length, this went from to, what is that, 11 minutes. So this is quite a bit faster. And it depends on, so not every model is set up to run in parallel, and not every model runs efficiently in parallel, but in this case it's a significant improvement. Still wouldn't necessarily try this if you don't have enough computing power, but it's trying to help us get there. Now what I want to do is walk through some of the options when training a model. And we're going to start to put a little control over that. Right now we're just using whatever are the default options in this train function for that particular method. So for the random forest, there are some defaults. It's running it with the train on those defaults. So some of those defaults make the machine run longer, others make it run shorter, and any choice you make can affect the outcomes of the model, but the more you mess around with it, the more you can kind of figure out what is a decent trade-off that works for you. Okay, so one of these, this is train control. This is how it is going to train the model on the training data set, and one of those methods we talked about in class, this cross-validation. So this repeated cross-validation, that's what this method is. There are some other methods. I think this is probably the most common and is the default. And you could try other ones that are just not repeated or other things. So it's fine. But probably this is most common. And then the options for these are the number of folds in the data. So this is how many times to split up the data. So in this case, it says the number is 10. So that means the training data set, split it into 10 pieces. And then it's going to go through, it's going to train the model on some set of those 10 pieces, and then test it on another piece of those 10 pieces. And then it's going to repeat this, do it again multiple times. Here it's going to repeat it 3 times. And this is sort of like running through over and over again to see if the model is fitting in a way that makes sense for the data. Well, if you do 10 folds and a lot of repeats, so let's say you did 10 and 10, that's going to take quite a while. Maybe something like 10 and 5 is a reasonable default. But if we want to not use up so much time, we can cut these down quite a bit. So here I used 3 folds and 2 repeats. Notice here I cut it down even more. So depending on how many times you make it go through the data, the more you do, the longer it'll take. So let's look at the example here. When I did 3 folds and 2 repeats, this was from 36 minutes to 38 minutes, so 2 minutes versus the 11 minutes it took up here. So a portion of that long time is coming from doing this repeating and multiple pieces of data. Okay, so we cut it down a little bit more. Let's try one more time. Well, if we go to 2 folds and 1 repeat, notice we went from 38 to 40 minutes, so that's 2 minutes. We didn't buy ourselves much time. It's fractions of minutes, so you could see that it made a little bit of a difference, but really cutting it down anymore doesn't seem to be helping a whole lot. But there's another piece that we added here, and so this is why it went from 38 to 40. So if I just ran this without trying anything else, it would be slightly faster. But we added a new piece. So the first piece was controlling how we're training the model. That's this train control, and it is input with this TR control option here. The other piece is this tune grid part, and the tune grid part deals with whatever parameters are there that you can change for the model itself. So for the random forest, one of the tuning parameter that we most likely want to try is how many columns to try randomly. So here it's saying mtry is the parameter we can mess around with. It's going to say try 1 column, 2 columns, and 3 columns. So this colon in the middle says 1 through whatever is on the right. So the starting number and the ending number. So this is going to try 1 column, 2 columns, and 3 columns. So this expand grid function is how you input the parameters that you are going to try, and you can limit this. You can make this even more. We could go 1 to 10. We don't have that many columns, but however many columns we have, you could change this. And then some of the other methods, so this random forest is fairly limited. Some of the other methods we're going to try have other options, so it's not always mtry, it might be something else. And so you have to look up each method and find out what those different tuning parameters are. But the benefit of this is this tune grid piece here, this option. So notice I did expand grid and then save that as the grid option. Up here I did train control, save that as the option. So notice this control goes into this train control option. You could just take this train control thing and put in here instead, but then it starts making the everything here get really long. So this is just for convenience here. Same thing with this expand grid. You can save it here as its own object and then just input it here, or you could just copy and paste this and put it into here as well. So either way it does the same thing, but this is just for convenience. So in this tune grid, we're fine-tuning the method that we're using to try and find the options, the parameters that are going to make the model work best. So if conceptually you could try every single possible parameter, and the caret package will try and work through, through this train function. We'll try and go through every possibility and find the one that works the best for the data you have. Great, that's, if you have all the time in the world, then that's fantastic. Or if your computer can handle it, that's fantastic. But often we just have to make choices and sort of see what matters. So let me walk through some of the different options here so you can get an idea of this. So here, the linear model, there's an intercept. You can have an intercept, yes or no. Not really, doesn't seem to matter that much anyway in a lot of things I've tried, so we won't really deal with that. If you're doing K and N, this is the K nearest neighbor stuff we did, related to what we did before, but this can be also a regression. The tuning parameter here is K. So up here, that's the number of neighbors you're going to use. So then in this expand grid, you would put K equals whatever you want to put in here. It could be, 1 to 3 like it is here. It could be 10 to 100. It could be sort of anything that matches your data. So then that would be the expand grid part. Notice the train control with all of these methods can stay the same across every method. If we're doing the XGB tree, this one has quite a bit more options here. So, and I've listed out sort of what they do, but if you wanted to mess around with the XGB tree, then you can just work on one of these options within that tune grid, but it depends on what you want to do. Or you can try all of these and just mess around with all of these. The more you do, so like here, the number of rounds, if you increase the number of rounds, then of course it's going to take a lot longer. The depth, so if you make the depth of the tree longer, bigger, it's going to take longer. These ones we haven't talked about, eta and gamma. These are sort of controlling how much overfitting is happening. This is a percent, how many columns to choose, sort of related to the number of tries. And then this is related to the max depth. It's how many to have at the end of the tree. So just some options. You could mess around with those if you wanted to do more with the XGB tree. And then the neural net. This is the average neural net. There are a few things you could try here too, decay, size, and bag or not. We won't go into the details of those, but you could try a few things here. So for example, this decay is a shrinkage parameter from 0 to 1, so you could try different things. In all of these that have something like this, it's trying to prevent overfitting the data, because this data can do this machine learning models can overfit the data really, quite well, which is a negative thing, but it's good at doing it if you let it. Size, this is related to how many units are in the hidden pieces of the neural network. So the larger this is, the longer it takes to fit, and the more complicated the neural network is, and then some other related stuff. So you can try these different things. I'm not, we don't have time to go through all of these, but it's worth trying a couple just to see what happens, and we'll do a little bit of that in class. But I wanted you to be aware of, so let's go back to the basic idea here. What can you control when you're doing this? Well, first we did the parallel processing just to help speed it along. But the things you can control are how you train the model. That's this train control. And the parameters, you can adjust the parameters that are used for each specific model. That's this expand grid. The nice part is the caret package with the train function will do that for you, and it will run through it all and then spit out what it thinks is the best. All right. So let's try one other piece. So one of the things that happens when let's say you don't know what the model should be. So here I have a random forest model, XGB tree, which is a type of, it's related to a random forest, linear model, which we've already talked about, and then this average neural net. I liked this extreme learning model, but for this version of R, it doesn't work. The author didn't keep it up yet. So we're just going to do these ones here. And remember, there are lots of different models you can look at, and you just have to go look on the website and kind of learn about it. But I tried all of these. So one of the problems, again, with machine learning models, there are a couple things. One, you don't know what the correct model is. So this could include what you put in the model, and this could include the modeling method. You don't know what's the right thing. So one of the approaches to dealing with that, one is you just keep going through every model and try and find what's best. Another is to do what is called model averaging, or ensemble learning models. And an ensemble model just combines models combines different models. And so then you use these different models, combine them, and see how well that predicts. One of the things that helps somewhat with overfitting that might be specific to an individual model. And it helps, more importantly, I think, with not knowing what the correct model is. So if you're really not sure and there are different models, combining them could help you when you go to actually do the prediction. So I ran this. Notice this is 20 minutes about to run all of these together, and this is still running in parallel. So it takes a little while here. I use the fairly standard 10 folds with 5 repeats. That's sort of standard. Ran that 20 minutes. Then how do we do the ensemble method or the model averaging? We're going to first we need to know what each of the predictions are for all of these here. So on the training data, this is one time we'll use the training data and predict. So on the training data, what was the predicted value for the first model, the second model, third model, fourth model? Combine them together to create this prediction. Then the problem is we want to weight each prediction and try and choose how much to value the random forest or the XGB tree or the linear model. And so it's trying to trade off among those to find which one works the best. So in terms of the training data, whichever has the highest R squared, whichever one is fitting the data the best is going to be the one that it thinks is the most important. So in terms of ensemble methods, I don't know that we get a whole lot out of understanding that on the training data. So this is really something that I would apply on going to the testing data, but we can set it up this way. So we get these training predictions, now use some other model, doesn't really matter. So notice I've got all the X variables predicted 1, 2, 3, and 4. Those are going to be the variables I'm going to use to now predict ROA lead 1. Okay, so I'm just doing another model. I'm going to use random forest here. It could be anything that you want to use. And I'm going to try and predict then ROA lead 1 with what I predicted using these other models. So this is going to look really good because we're using data about the future ROA when we're creating this, but then when we move out of sample, it's going to be different. So then I could do the same thing now and say, now that I have these variables in here, I could predict using the ensemble model with the training data what I'm going to call the prediction, the 5th prediction. Okay, so I've got different predictions. 1 is the random forest, 2 is the XGB tree, the 3 is linear model, and 4 is the average neural network. And then 5 is the ensemble method. So then how do these work in sample? Well, we could look at the model. So the caret will output something from the model. So if I run est1, it tells me it tried 2, 3, and 5 as options for how many columns to try in the in tuning the model. It selected 2 as the best, and the R² here you see is 60, or 0.6 or 60%. Then the second one we get 57, third one we get 38, fourth we get 59. So these ones, the worst is this linear model. The random forest, it seems to be the best, but the random forest and the neural network are really close. The XGB tree is close as well, but slightly underperforms these two. Then we get this 0.96 for the ensemble method. Well, that's a little cheating because we already have ROA, the predictions here were already trained using what the prediction was, so we're cheating here. So it doesn't really tell us much here, but you can see what it is. Then we can look and see what the different variables are that matter the most. So for 1 and 3, this is, for 1 and 2, this is total assets. So the tree methods get the log of total assets. The third one gets ROA. This is the one that performs the worst. The neural network one doesn't have a function like that. And then the variable importance, or it doesn't work with what we have. And then the ensemble model chooses the first prediction as the most important, which is what we've sort of already seen here as having the highest R². Okay, so we do all of this, and this is supposed to help us evaluate these models. So before we move on to evaluating them in the testing data, we have to be sort of confident that we have done what we hope we could, and we are no longer going to train this. So if we weren't satisfied, and by the way, these are reasonably good R²s. You know, with a lot of accounting data, it's really difficult to get something much better. So I'm, fairly confident we're not going to suddenly get something better than this. But if we weren't satisfied with this, we could go back, way up here and say, okay, we have these variables, but I'm not satisfied with what we have right now, so we need to get more. So we could go try and improve these variables that we have, maybe clean them up more, measure them differently, or go collect more variables to try and predict it better. And then we could go back to this training and see, is everything we've done, if we've done it correctly, are we any better off than sort of where we are now? And, if you do, then okay, you keep doing this and you keep fine-tuning this. And it's also possible that, let's say, we just used here the XGB tree, the defaults for the grid. And notice on all of these, I left the grid defaults, the grid as the defaults. But we could go back and use different grids here. So, up here where we were trying the mtry 1 to 3, well, we could go down here and change this random forest to incorporate those different attempts. Same thing with XGB tree. It may be that this is slightly worse because we haven't trained the right grid or the right parameters, so we could go back and adjust this. Same thing with the neural net. So we keep trying some things until we figure out what we are happy with, and then we can go ahead and look here, and if we're happy, then we go ahead to the testing data. One thing I forgot to mention is if you're using the neural net, so each of these has different features that we have to be careful with. If you're doing the neural network ones, this lin out says that the outcome that you're trying to predict is a linear outcome or a continuous outcome. So ROA here is numeric, and it is not a categorical variable, so then we have to tell it true. For the tree-based methods, if this were categorical, then we need to put the left-hand side variable as a factor or character, and depends on which model we use, and you just sort of have to either read about it or try different ones. Okay, so then we finally get to, let's say we're happy with these, we want to take all of these predictions. Notice here we're just predicting, and the only thing we're doing is moving to the testing data. So now I have, for the testing data, I've got 5 predictions, and we're going to evaluate them the same way we did before. And the simplest way is, or at least from what we have, is do this prediction. We're going to use a linear regression of ROA on the prediction. And so this is the y variable we're trying to predict. This is what we predicted. And then we run this, and we can see what the r squared is coming out of this. We can just directly calculate r squared, or there's some other methods for testing, but this is, I think, the most straightforward and easiest for what we have. Okay, so then we look, and one of the things you notice is moving to the testing data set, all of the r squareds went down. This is because the model fits as best it can on one data set, but when we move to another data set, it's not quite as good, right? The model doesn't fit that data as well. And so it's very typical for r squared to go down some when you move to a different data set. It doesn't always have to happen, but this is sort of a general rule. And pretty much they all went down a little bit. Some went down more than others. The linear model hasn't changed a whole lot. So instead of 60% here, we're 52, and we've got 46 and 49 here. This is for the ensemble model. Notice it has gone down a lot, but that's because now we're not cheating here, so that makes sense. And notice it's sort of like an average of the other ones, and this is really typical as well. So, if you look across these r squareds, the ensemble model is just combining these different predictions, so it should be kind of somewhere in the middle of these other predictions, which is, sort of makes sense. And if the benefit of it is, if you don't know which to choose, then the ensemble model, gives you a way to sort of use those. But we still have a little bit of the ranking here where the random forest seems to be best, and the neural network slightly not as good, but pretty similar. Okay, so once we have these, we say, okay, we're good. We had already tested them. We had already trained them. Now this is our test, and seems to have worked the way we thought. Now we just start applying it, and this would be sort of real-time applications, or whatever thing you're going to use it for. So notice here I have the testing data set. So I can compare what actually was there, and that's what these r squareds are doing, compare what actually happened to what I predicted. If you're in real time, you would predict and then see what happened with it. So here I have what actually happened, here I have the prediction. So I could call this something like unexpected ROA. So if I predicted it was going to be 100, well, that's not an ROA. If I predicted 10% and it actually ended up being 20%, then I could say that it's higher than expected. Okay? So how do I use this? Like if we think about the project, so if we wanted to say these are higher than expected, we could then go in and sort the data and look at those that are the most unexpected, the highest unexpected to the lowest unexpected. So I just sorted it here. And then I did if you use head, that'll just give you a piece of the data, the top of the data. And these are the most unusual, unexpected, and we see that ROA is quite high, so 60% here, but the ROA in the prior year was minus, quite large, so this is much higher than expected. We have some others. This was very negative, and this is slightly higher than expected. Notice all of our top ones were ones that had very low performance in year T, and higher in year T+1. So if we wanted to fix this, right, we could, having these ones that are so negative that are not really in terms of like a return on assets, these are numbers that we don't really expect, we could perhaps go back and get rid of some of those, or only look at the unexpected ones that had ROAs that are in a range we might be happy with. All right, so mess around with it. You try and come up with a reasonable prediction, and then let's say you're done with it. Then you need to stop the cluster. So this function stop cluster, notice CL was the cluster name we used up here. That's this right here. So we're going to stop it. So you run this, and you can unregister. That is trying to remove it. Oh, sorry, I have this in the wrong order because I had it there before. So we're going to stop the cluster. This unregister is what if this cluster still hangs on. So if you try and run caret after stopping the cluster, sometimes it'll tell you there's an error because I can't find a cluster because the caret function is trying to use, or the caret package is trying to use it. So one of the workarounds here is to use this function that someone wrote, and this was to go through and find anything that might be related to it to get rid of it. So you could do this. This is the function, then you run the function, and that'll close out anything that it finds. That is if it doesn't seem to get rid of it. So that's the main issue. So, all right, so again, practice these things, mess around with it, and see how, work on trying to come up with a model that makes sense to you. And I think the more you mess around with it, the more you can learn about each of the pieces and see what they do. And we'll do some of this in class as well. All right, have fun with this.